This presentation deals with sections 7.3 and 7.4 in your textbook. We've already looked at two different ways to solve systems of linear equations. We looked at graphing two lines and finding the point where they intersect, and then we looked at substituting information from one equation into the other to find the coordinates of the points where those lines intersect. These next two sections deal with two additional methods to solve linear systems. Our goal is still to find the coordinates of a point where two lines cross. In other words, to find a point whose coordinates are solutions to two different equations at the same time. Section 7.3 shows how to use addition to do this, and section 7.4 shows how to use multiplication to do this. There's an old saying that says, there's more than one way to skin a cat. And while this may sound gross, and a reasonable question to ask is why you would want to skin a cat in the first place, what this expression really means is that there's multiple different ways to get to the same end goal. And just because sometimes you need visuals to help you with things, here's a visual to help you with this lesson. Okay, on to the math. Shown in green here is a system of linear equations. The first equation is 5x plus y equals 8, and the second equation is 2x minus y equals 4. We're going to take one of these equations and look at operations we can do that keep that one equation balanced. In the past, we've added the same thing to both sides of an equation, and that didn't change the solution to the equation. It made it look different, but it didn't change its solution. So for example, if I take the first equation, 5x plus y equals 8, I could add 4 to both sides, and that would give me a new expression that would have the same solutions as the original expression. My new expression might look kind of weird, but it would still have the same solutions. Similarly, I can take 5x plus y equals 8, and I can add the same thing to both sides of the equation, even if the way I write that same thing looks different on the left than it does on the right. For example, what I've shown here is that on the right-hand side, I add a plain old 4, and on the left-hand side, I add an expression, 2 plus 2. Why is this okay? Well, 2 plus 2 and 4 are equal. It's just two different ways of writing the same quantity. So what I'm really doing is I'm really adding the same thing to both sides of this equation. Again, it's not going to change the solutions to this equation. Now you might ask yourself, that looks like a really weird way to add 4 to both sides. Why the heck would you do that? Well, here's where we're going with this. I can take the first equation, 5x plus y, and I can add 4 to both sides of it. Notice the second equation tells us that the expression 2x minus y is equal to 4. The 2x minus y is another way of writing 4. So I can take the first equation, 5x plus y equals 8, and I can add the second equation to it. What I'm really doing here is I'm adding 4 to both sides of the first equation, but I'm writing 4 in two different ways. I'm still adding the same thing to both sides of the equation, I'm just writing it differently. When I do this, when I add these two equations together, notice what happens. On the left-hand side of the equal sign, we had a positive y and a negative y. When I add those two together, the y's add up to 0. The y terms drop out, and I'm left with a single equation with a single variable, 7x equals 12. I can solve that equation for x, and that will tell me the x coordinate where the two lines shown in green intersect. Here's an example of how to use this process of adding two equations together to eliminate a variable. Suppose I give you the example above. 2x plus 3y equals 11 is the first equation, and negative 2x plus 5y equals 13 is the second equation. If I simply add these two equations together, remember what I'm really doing is adding the same thing to both sides of the first equation. When I add these equations together, what I get is that the 2x term in the first equation and the negative 2x term in the second equation will add up to 0. The x terms will drop out, And what I'll be left with is an equation with a single variable. 8y equals 24 in this case. I can solve that for y, and I get y equals 3. Now I know the y coordinate of the point where the two original lines cross. I take that y coordinate and I plug it into either equation 1 or equation 2 above. It doesn't matter, because remember, the point I'm looking for has to be a solution to both equations. So I plug that in. Either equation is fine. I'm going to choose to plug it into the first equation. I'm going to substitute 3 for the y in this first equation, and I'll have 2x plus 3 times 3 equals 11. When I simplify that and solve for x, I'll get that x equals 1. So the x coordinate of our solution is 1. Don't forget the very last step, which is to write that x and y coordinate you found in a coordinate notation, so we remember that we found a point where the lines cross. So these two lines cross at the point 1, 3. 1, 3 is a solution to both equation 1 and equation 2. Here's another example. In this case, we're going to have to use subtraction to eliminate a variable. So we have equation 1 that's shown above, 4x plus 3y equals 2, and equation 2, 5x plus 3y equals negative 2. If I simply added these two equations together, neither the x variables nor the y variables would drop out. However, I noticed that the first equation has a 3y and the second equation has a 3y. So if I subtract the second equation from the first, then the variable should drop out. Let me show you what that looks like. I'm going to take the first equation and I'm going to subtract off the second equation. I'm subtracting the same thing from both sides. One of the most common errors to make in Chapter 7 is when you subtract one equation from another, taking care to make sure that you're subtracting all of the terms in the second equation from the first. Watch your signs in this one. So I have 4x minus 5x, that gives me negative 1x. I have 3y minus 3y, so there's no more y's, the y's have dropped out. And on the right-hand side of the equal sign, I have 2 minus negative 2 minus a negative is the same as plus a positive. So the resulting equation is negative x equals 4. Notice that I only have one variable now, and I can solve for x. When I do that, I get that x has to be negative 4. Now I take that x coordinate, negative 4, and plug it into either equation above, doesn't matter which one, to solve for y. I'm going to plug it into the first equation. I'm going to replace the x with negative 4, and then I'm going to solve for y. When I do that, I'll get that y equals 6. So the coordinate that satisfies both equations, the point that is on both lines, is negative 4, 6. Now you've learned a couple different methods to solve a system of linear equations. Graphing in general isn't terribly reliable because it's hard to tell exactly what the points are by looking where two lines cross. So you're most often going to be using substitution or addition. And it's a reasonable question to ask, how do I know which method is going to be the most efficient, is going to get me to the right answer with the least amount of work? Well, here's a tip for how to decide whether to use substitution or addition. If there's already a variable all by itself on one side of the equal sign, substitution might be the easiest method. Here's an example. If you have a system of linear equations that looks like this, 6x plus 3y equals 12 is the first equation, and x equals y plus 1. Notice that in the second equation, x is already all by itself on one side of that expression. And so we have x is the same thing as y plus 1. So I can replace the x in the first equation with the expression y plus 1. When I do that, I get 6 times the quantity y plus 1 plus 3y equals 12. Notice this equation only has the variable y in it, and I can solve this to find the y coordinate of the solution. The reason it was easy to plug in here is because we already had x all by itself. If there is what I call a matched pair of terms, then either addition or subtraction might be the easiest. Here's an example. We have this system of equations, 6x plus 3y equals 12, and 8 minus 3y equals 2x. Notice that in the first equation, we have a positive 3y, and in the second equation, we have a negative 3y. That's like a matched pair of terms. They have the same coefficient and the same variable. In this case, if I add the two equations together, those matched pair of y terms will cancel out. The y's will drop out. So look for, do I have a matched pair of terms already? Because when I add those two equations together, on the left I would have 6x plus 8, and on the right 12 plus 2x, and the y term simply dropped out. A couple of tips to help you if you're solving systems of linear equations by addition. You want to start by arranging the two equations so that like terms are in columns and that the equal sign is in a column. Here's what I mean. The original problem shown here says 4x plus 5y equals 35 for the first equation, and the second one says 2y equals 4x minus 7. I'm going to leave the first equation as it is, with the x term first, the y term second, and the constant term, 35 in this case, on the other side of the equal sign. I'm going to rearrange the second equation. I'm not going to change the solutions to it, but I'm going to rearrange the terms in it. I'm going to subtract 4x from both sides of the second equation. When I do that, what's going to happen is that my terms in the second equation are going to line up in columns with the terms in the first equation. So when I subtract 4x from both sides, I get this new expression, negative 4x plus 2y equals negative 7. Notice that when I place that underneath my original equation, the negative 4x term lines up with the positive 4x term above. The 2y term in the second equation lines up with the 5y term in the first equation. The equal signs are lined up, and the constant terms are on the right-hand side of that equal sign. This makes it easier when I go to add these two equations together to simply add the like terms in each column. When I do that, I'll see that my x terms disappear because I have 4x and negative 4x added together is no more x's, and I'll have 7y equals 28. A reasonable question to ask is, what if we don't have a variable all by itself, or we don't have a matched pair of variables? In other words, what if the two equations don't add or subtract together nicely to have a single variable drop out when we do that? Shown at the left is an example of a system of linear equations, and notice that we don't have any variables already by themselves on one side of the equal sign, and we don't have a matched pair of variables. What can we do in this situation? Well, remember that it's okay to multiply both sides of an equation by the same thing. So for example, if I take the first expression at the left, 5x plus y equals 8, it's okay to multiply both sides of this equation by 2. When I do that, I would get a new equation, 10x plus 2y equals 16. The solutions to this equation, in other words, the line that represents all of the xy pairs that make this equation true, are the same as the solutions to 5x plus y equals 8. When we multiply both sides of an equation by the same number, we don't change the solution. So what I've done is I've written the equation of the line 5x plus y equals 8 in another way. How is this helpful? Well, what I've done is I've created a matched pair of variables. The resulting equation after I multiplied both sides by 2 has a 2y term in it. This matches up with the negative 2y term in the second equation. So now my system of linear equations looks like this. 10x plus 2y equals 16, and 2x minus 2y equals 4. Now I have a matched pair of variables, and I can simply add these two equations together to get rid of the y terms so I can solve for x. Let me show you an example problem and we'll work through this. Equation 1 is 6x plus 5y equals 19. Equation 2 is 2x plus 3y equals 5. There are no matched pairs here, but I'm going to notice that if I multiply equation 2, if I multiply it through by -3, what that's going to create for me is a matched pair of x terms. I'll have a positive 6x term in the first equation and a negative 6x term in the second equation. So I'll leave the first equation alone. I'll take the second equation, 2x plus 3y equals 5, and multiply everything in it by -3. When I do that, the first term, 2x, becomes negative 6x. The second term, 3y, becomes negative 9y. And the constant term, 5, becomes negative 15. I multiplied everything on both sides of the second equation by -3. Now my system of linear equations has a matched pair of variables, 6x and negative 6x, and I can simply add these two equations together. When I do that, when I add those two equations together, I get negative 4y equals 4. The x terms dropped out. Step 3 is to solve for y. When I do that, I get that y equals -1. Now I need to plug that y value back into either equation, doesn't matter which one, to solve for x. I'm going to pick the second equation, and notice I'm using the original form of the second equation. I could, in fact, if I wanted, use the resulting equation after I had multiplied through by -3, because those two equations will have the same solutions. I'm going to plug y equals -1 into equation 2, and then I'm going to solve for x. When I work through that, I'll see that I get 2x equals 8, and when I divide each side by 2, I get that x equals 4. So the x coordinate of my solution is 4, and the y coordinate of my solution is -1. Here's another example. I can solve this system of linear equations, 4x plus 5y equals 35, and 2y equals 3x minus 9. This is a case where I probably want to rearrange the terms in one equation or the other so that they line up in columns. So the first thing that I'm going to do is I'm going to subtract 3x from both sides of the second equation. When I do that, my second equation becomes -3x plus 2y equals -9. Now I have my like terms in columns, and I can continue on to see if I can add these together, subtract them, how I can eliminate one of the variables. What I'll notice in this case is that I have two equations, and it's not as though I can take either one equation and simply multiply it through by a constant to get a matched pair of variables. So what I'm going to do in this case is I'm actually going to multiply both equations by something. I'm focusing in on the y terms right now. I have a 5y and a 2y. And I'm asking myself, what can I multiply the equations by so that I have a matched pair of y terms? Well, the lowest common multiple of 5 and 2 is 10. So if I could get both of these equations to have 10 y terms in them, I would be able to either add or subtract the equations together to remove the y terms. What I'm going to do is I'm going to multiply the first equation through by 2. That'll give me 8x plus 10y equals 70 for the first equation. And I'm going to multiply through the second equation by -5. When I multiply it through by -5, I get 15x plus -10y equals 45. Notice that I've created this matched pair of variables, positive 10y in the first equation and negative 10y in the second. Now I can simply add these two equations together and the y terms will drop out. When I do that, I get 23x equals 115. I'm going to solve that for x by dividing both sides of the equation by 23, and I get that x has to be 5. I take that x coordinate then, and I'll plug it back into any of my original equations. And when I do that, I'll solve for y, and I'll get that y has to be 3. So the solution in this case is the point 5, 3. The x coordinate has to be 5, and the y coordinate has to be 3.